Want to talk a little bit about kinetics and about rates. Has nothing to do with rats. And I thought perhaps rates, well, obviously, one thing that is very nice in terms of rates is a practical example. First of all, what is a rate? What is rate defined as? Anyone? Give you an example. Miles per hour. Change in something over time. I like that. But it's not the definition of a rate. Is miles per hour, is that a rate? Yeah? Okay. Is watched hours of television per week, is that a rate? No? No? Not? Watched hours television per week, is that a rate? No? You go, no, it's not? Mm-hmm. Eaten donuts per academic staff, is that a rate? Teenage pregnancies per 1,000 secondary school students, is that a rate? Oh, some, no? Yeah? Maybe? Is that a rate? No? What I've just given you are examples, are all examples of rates. Sorry. A rate is basically defined as something divided by something else. So if you have, for example, donuts eaten per academic staff on a party, that would be a rate. What is speed? I mean, not the stuff that you know, that you take. What is speed? Change in velocity over time. What is speed? It is just something. What is the difference between speed and velocity?
Velocity has direction.
Velocity has a direction. Speed doesn't. Speed is, in a way, a change of something per time. Yeah? Is speed a rate? Loud? Yes, because it is something per something, right? So speed doesn't have a direction, whereas velocity does have a direction. So you can have, can you have a negative speed? No. Can you have a negative velocity? Yes, you can have a negative velocity. If my velocity is defined as how fast I get from here to here, then that is positive. If I do the reverse, then I have, per definition, a negative velocity. Both might be the same, but one has a positive sign, one has a negative sign. Okay? Now, okay, we've clarified that. Usually, we can, when we speak about a rate or velocity of something, we usually use this interchangeable, although we want to be clear that it's not interchangeable. And usually in a biological and chemical context, we are talking very often as rate equals as a change in, let's say, concentration per time. Okay? And of course, a rate has one thing in common with velocity. A rate can also have a direction. So that would be a rate. Velocity is pretty much the same. Equals, again, change in concentration per time. What could be the unit for velocity in this case? What do you reckon? What could be a unit for that? Sorry? Moles per second, exactly, because we have, bless you, we have a concentration here that it would be, concentration would be molar, exactly. So molar per second. Or it can also be a change in amount of something. So then it would be mole per minute or something. Yeah? That makes sense? Now, let's say we have a reaction where we have, say, A. This is our reactant. And this is then converted into something else. We can very often write in this case the general, what is called the general rate equation. And this is basically rate equals. Now, what we have here is the consumption of something. We consume A. And when we are talking about a consumption, then consumption indicates that something is taken away. If something is taken away, it's usually a negative thing, right? If I take away your money, that's not good for you, is it? That's negative. So therefore, if we are talking about a consumption, the whole thing will be negative. We can write rate equals negative a rate constant, and this rate constant here is abbreviated as a K. It's not because I have got problems with writing a C, but C means the speed of light. And most of these equations were developed by Germans, and Germans just simply spell constant with a K. So that's where this K comes from. So rate equals consumption, negative, K times usually the concentration of A, and I put that in brackets, in square brackets, to indicate that this is a concentration. And sometimes we need to put up a sort of an exponent on that. And this exponent actually is called the rate order of the reaction. Now what you see here is the general rate equation. Rate equals minus k times, oops, I made a mistake.
The screen's frozen.
The screen is frozen. I don't like that. Thank you. Okay. Are we back in business? Yes, we are. Yes, thank you. So this is the general rate equation. Rate equals minus k times a to the power of m. Okay? Now, this rate equation is, bless you, only a mathematical concept. It tells us how we can describe this particular reaction. Only a mathematical concept. It doesn't tell us anything else. Now, let's have a quick look at this k and this m. So I said k equals rate constant. Oh, what? What is going on here? Let me see if I can. Okay. K, yeah, is rate constant. And a constant is always a constant, it doesn't change. Also, the rate constant is always, without any exception, always a positive number. It cannot be a negative number. So whenever you do any calculations with rate constants, it has to come out as something positive. If you get something negative, you can be sure as hell that you made a mistake somewhere. M indicates the rate order. Now, M can be basically any number that you want. Can be anything. It can be a whole number. It can be a fraction. It can be a positive number. It can be a negative number. It can be 0. And we will discuss special cases where m is 0 and 1, for example, or 2. So there's no restriction on that. So what does m tell us, actually? M just simply tells us that it is the order of the reaction. A lot of people get this mixed up with what is called the molecularity of a reaction. A molecularity simply means how many atoms or how many particles actually crash into each other at the important moment, at the slowest step, if you like. Now, can you have a molecularity of 0, given this definition? Can you have 0 atoms being involved in a reaction? Can you? No. Can you have 1 atom or 1 molecule being involved in a reaction? Yes or yes? Yes, exactly. Didn't give you any options, did I? 1. So something can have a molecularity of 1, which means 1 molecule is directly involved in this reaction. Can you have 2 molecules? Yeah, if 2 molecules crash into each other. Can you have 1.5? Can you have 1.5 molecularity? Can you have half an atom? Not really. So 1.5 is not an option. 1.3 is not an option. It has to be whole numbers molecularity. Unlike the order. Order can be anything. Can you have 3? Molecularity of 3. Yeah? In theory, you can have 3. However, to my knowledge, there's only 1 extremely exotic reaction has ever been observed where 3 molecules actually have to crash into each other at the same time to make things happen. It's an extremely rare event. So 3 is possible, but extremely rare. And molecularity of 4 has never been observed. It is theoretically possible, but so far, and people have looked, so far we have no example for that. So it's usually either 1 or 2, the molecularity. The order can be anything. Order is only a mathematical concept. Does that make sense so far? Yeah? Okay, then let's do a simple reaction. Let's say we have a compound called S, and this compound is consumed. Right? S could stand for substrate. This reaction might be driven by an enzyme. And people have tried to figure out a description of this equation, a description for the rate of this equation, I should say. They found rate equals, and in a way, people do something really naughty, because we said rate, it has a direction. But because biochemists and bioscientists in general are a little bit lazy with signs, they just simply said, oh, that's the same as the speed. And therefore, they just simply ignored the positive and negative stuff. But they found, and there were a number of German scientists, actually, who did that. One was called Michaelis, the other one was called Menten. They found that they can describe the rate of this enzyme catalyzed reaction by an equation. So rate equals something that they defined as Vmax, the maximum speed that this enzyme is actually able to work, times the substrate concentration, divided by Km plus the substrate concentration. Now that was basically their empirical finding. They could describe the speed, or more sloppily, the rate of this enzyme reaction with this equation here. Does that sound familiar, this equation? Have you seen that before? Have you? No? Yes, you have seen that before, haven't you? Have you seen it before? Yeah? Oh, you are a bioengineer. That's why you haven't seen it. Sorry. This is the famous Michaelis-Menten equation, which describes how the speed of a reaction is linked to the substrate concentration. There are certain conditions for that, but we are not going into that because you are doing that in BI 301. Now, when you look at that, and when you plot conventionally, what do you plot? I'm not going to ask you about that. What do you plot usually for a Michaelis-Menten plot? Michaelis-Menten plot. What do you plot on the x-axis? Are you bioengineers? No. It's the substrate concentration, exactly. What do you plot on the y-axis? The velocity. So that would be rate, speed, or velocity. Okay? Happy with that? And what you usually get is something like that. Is that correct? Yeah? The typical Michaelis-Menten plot. Of course, Michaelis-Menten plot is pretty shite. Why is that? Why is a Michaelis-Menten plot really bad? It doesn't tell you Vmax or Km. Let's just quickly revisit. What is Vmax actually? Vmax is the maximum speed at which the enzyme can actually work. It's a little bit like a Ferrari. It tells you, in a Ferrari, it says, it can go 250 miles an hour. That's the maximum speed. Unless you do a little bit of fine-tuning and put in some rocket fuel or something like that. But even then, there are some limitations. That's the maximum speed. You said Km. What on earth is Km? Loud? It is, you are absolutely right, Seamus, it is the substrate concentration that leads, or that results, bless you, in half of Vmax What's the unit for Km? Loud? What's the unit for Km? Somebody said it already. I heard some. Molar. You are absolutely right. It's molar. It's the same thing as the substrate concentration. Km is always molar or millimolar or micromolar or God knows what molar, but it's always molar. Yeah? Oh, for fuck's sake. Excuse my language. That is Km. So Km is always a concentration. What does, again, let's have that in a slightly different context. What does Vmax tell you? Vmax tells you how the enzyme behaves at very, very, very high substrate concentrations. Km tells you how much the enzyme likes the substrate. And usually, low Km means mutual love for the substrate. Low Km means you need only diddly squats of the substrate in order to get the enzyme going. High Km means doesn't like the substrate. You need loads and loads of the substrate in order to get the enzyme going. There's one more thing, which is the third enzyme parameter, and that is called Vmax over Km. And this guy tells you how the enzyme behaves at very, very low substrate concentrations. So these are the three parameters, Vmax, Km, and Vmax over Km. Now, unfortunately, the Michaelis-Menten plot, V versus S, doesn't tell you anything. It doesn't give you really a Vmax, because the Vmax could be like that, could be like that, it could go like that, could go like that. It doesn't tell you anything. If you don't have a Vmax, you can't calculate half of the Vmax. And if you don't have half of the Vmax, you don't have a Km. You can't say anything about the affinity of the enzyme. And that is simply because you can't really interpolate a curve. So that's why some people came up with a very clever idea of transforming a curve into a linear straight line. Because a straight line you can easily extrapolate. That makes sense? So, let's have a look how we can extrapolate and convert the Michaelis-Menten equation into a straight line. Have you done that, the extrapolation? Have you done the how you can transform that into a linear? You think so? It's very easy. What you do is you just turn this equation upside down. You do it 1 over. 1 over v, 1 over the rate. What you do to one side, you do to the other side, 1 over the right-hand side. So what do we get? On the left-hand side, we have 1 over v equals, now we have 1 over v max times s divided by km plus s. And if you remember how we divide a fraction, we just turn things round. So we would end up with km plus s divided by v max times s. Okay? Happy with that? And obviously this is a little bit of a mess. So what we can do is we can split this fraction equals km over v max times s plus s over v max times s. I'll just split this fraction in the middle. What you see here very nicely is the s cancels out. So that's good. And I can write this part here in a slightly different format. I have 1 over v equals, I can write it as km over v max times 1 over s. Yeah? Plus 1 over v max. Have I made a mistake anywhere? Mathematically? No? Looks good? So does that help us in any way? Actually, it does. Because otherwise, I would be totally stupid wasting time on showing you that. How does it help us? Well, y equals mx plus c. What's that? Equation for that? A straight line, exactly. So m, that's this one here. X is this one here. 1 over v max is the intersect. So what do we plot? We plot 1 over s, that's our x. We plot 1 over v, that's our y. Now, does the line go up or go down? What do you reckon? Up. Why? You're absolutely right, but why?
Because as you add more substrate, you get higher.
Do it mathematically. When does a line go down? When m is? When m is negative, exactly. When m is negative, the line goes down. Now, Km is positive, Vmax is positive, it must be positive. So therefore, the line goes up. Yeah? So we have, we have a line that goes up. We also know our C, that is 1 over Vmax. That's here. That's the intersect. We know that the line goes up. And we know that the gradient, our m here, is this Km over Vmax. Yeah? So that's the gradient. The intersect is the 1 over Vmax. And if we go back, thank you. And if we extend this line here into the negative range, this point here is actually negative 1 over Km. And this is your Lineweaver-Burk plot. Right? So with this little trick, you converted a curve into a straight line, which makes it much easier to extrapolate. Of course, you have a bit of a problem with a Lineweaver-Burk plot, because instead of Vmax, it gives you only 1 over Vmax. Instead of Vmax over Km, it gives you the reciprocate, Km over Vmax. And instead of Km, it gives you negative 1 over Km. But once you've got numbers for this 1 over Vmax, your calculator can deal with converting that back. Does it make sense? So that is your Lineweaver-Burk plot. I personally think that a Lineweaver-Burk plot is probably as useful as a chocolate fire guard. I hate Lineweaver-Burk plots because they are pretty crap. If you want to know why I think they are pretty crap, go to YouTube, go to my channel, and find the video about Lineweaver-Burk plots. Much better plot is an Eddie-Hofstade plot. And it's much more, how shall I say, exam-friendly, because for a Lineweaver-Burk plot, you have to do 2 calculations. You have to calculate 1 over the substrate concentration and 1 over V, 1 over the rate. With an Eddie-Hofstade plot, you have to do only 1 calculation. Much easier. Anyway, coming back to kinetics, where we started, one thing with enzymes is you can write them in a similar way. We said rate equals negative K times, let's say, S to the power of m. And when we apply this to enzyme kinetics, there's one of the really, really fascinating things. In enzyme kinetics, in a way, with this very innocent equation, V equals V max times S over Km plus S, looks pretty innocent, doesn't it? There's nothing special about it. When you analyze that in kinetic terms, what you will find is that it really, really messes with your brain. Because what you find is that K, our rate constant, is no longer a constant. It actually will change constantly It depends on S. A blooming constant that is no longer a constant. It's probably not worth the name constant. But it gets even worse. It gets really, really bad. Because M, our rate order, is not fixed. It also changes. Depends, again, on S. So this Michaelis-Menten reaction is one of the really, really fascinating cases where you just simply can't describe it with normal kinetics. I have to say, I absolutely love it, because it is really an intellectual challenge. The rate order and the rate constant both depend strictly on the substrate concentration. And so time. I think I better stop here. But just as a sort of a little thing for you to think, M becomes 0 when the substrate concentration is very, very high. And M becomes 1 when the substrate concentration is extremely low. So in a way, M proves that there is no certainty, no stability in this world. Bloody M. Have a lovely weekend. See you next week.